There are certain things in the universe that seem like they simply shouldn't exist. Not according to physics, not according to logic, not according to everything we've learned from centuries of stargazing, mathematics, and careful measurement. And yet they do exist. We have seen them, measured them, charted them in peer-reviewed journals, confirmed them through independent data streams, and still we find ourselves staring at our screens or telescope readouts, thinking, this cannot be real. These are not speculative stories, not thought experiments or sci-fi daydreams. These are hard observations, recorded by professional instruments, reviewed by professional minds. Each one has passed the threshold of doubt and become something far stranger, a mystery that science has accepted as real, but cannot yet explain. These things keep astronomers up at night, not because they are frightening, but because they are confusing. They don't break the laws of physics, exactly, but they do seem to hover right at the edges, like distant silhouettes in a fog, shadows that hint there might be more laws than we currently know. So tonight, let's take a gentle journey through the wildest of these mysteries, real data points that exist out there in the sky right now, quietly defying everything we think we understand. But before we dive into the deep unknown, a quick ask: if you enjoy videos like this, a like or a subscribe would help more than you know. Thank you. And now, let's begin. We start in the summer of 1977. A radio telescope named Big Ear, stationed in Ohio, was quietly sweeping the sky as part of an early SETI search for extraterrestrial intelligence program. Its job? Listen, continuously, endlessly, hoping that, maybe, somewhere out there, someone else might be transmitting. One night, as the telescope recorded its usual data stream, it caught something odd, something that didn't belong. A clean, narrow-band radio signal. Loud, focused, sustained. It lasted for about 72 seconds. It wasn't background noise. It wasn't random. It came from deep space and then disappeared. It was so clean, so anomalous, that the astronomer reviewing the printout, Jerry Amon, circled it in red pen and wrote a single word beside it: wow. Since then, it's been known as the WowSignal, and even now, nearly 5 decades later, it remains among the best candidates for an artificial radio transmission ever recorded. Let's break down why this is so strange. First, the frequency. It arrived at around 1420 megahertz. That's the hydrogen line, the most common element in the universe. A logical frequency for any hypothetical alien civilization to use if they wanted to send a signal meant to be noticed. Second, the bandwidth. The signal was incredibly narrow, just a few kilohertz wide. Natural sources usually spread out. This was focused, sharp, as if beamed intentionally. Third, the duration, about 72 seconds long, which fits neatly into the rotation window of Big Ear's scanning method. It came, it peaked, it faded, all exactly as it should have if the signal was coming from a fixed point in the sky. Everything about it felt engineered. And yet, here's the haunting part: we never heard it again. Ever. The same region of the sky has been scanned hundreds of times since, by more sensitive telescopes, by better computers. And yet, silence. Nothing like it has been detected since that day. So, what was it? Let's talk through the hypotheses. Could it have been a satellite? Unlikely. The signal matched a fixed sky coordinate, not a moving one. Could it have been a reflection from Earth? Big Ear had 2 beams that would have picked that up. Only one recorded the signal. Could it have been a star or planet? They don't emit in that frequency range. For decades, the most serious natural explanation was that it came from a comet, specifically the hydrogen envelope around certain icy bodies. But when those comets were checked later, they weren't anywhere near that sky region during the signal's arrival. And even if they had been, no comet has ever produced a radio signal with that strength or precision. To this day, there is no known natural source that can fully account for the WOW signal's characteristics. And so, it lingers, a single moment frozen in red ink on an old printout. The closest we've come so far to something that looks like a whisper from the dark. Now, maybe it was just noise. Maybe it was a cosmic fluke we misunderstood. Maybe our instruments back then were more fragile than we remember. But maybe, just maybe, it was real. A deliberate message from a civilization so far away, so fleeting in time, that it never had the chance to say more than a single word. Wow. And then it was gone. It's important to be clear. Mainstream astronomy doesn't claim the wow signal came from aliens. Most scientists lean toward it being an anomaly we haven't figured out yet. But what makes it fascinating, what makes it linger in the minds of astronomers even today, is that it remains unsolved. Not disproven, not debunked, just unexplained. And that's what this video is about. One anomaly alone might be noise. But what if there are more? What if our sky is full of things like this? Not just one wow signal, but dozens of phenomena that hint, whisper, or scream that our understanding is incomplete. Things we can measure but not explain. And so, let us continue. Next, we'll visit a star that dims in a way stars shouldn't dim. It doesn't blink like a planet transit. It doesn't flicker like a dying sun. It fades erratically, dramatically, inexplicably. And it has scientists wondering if something impossible might be orbiting around it. That's next. Please like and subscribe because this journey will change how you see our place in the universe. Prepare yourselves. We begin. Imagine watching a distant star slowly fade, not just flicker or shimmer, but drop in brightness like someone pulling a curtain across a light bulb, except the curtain doesn't move predictably, and the light never dims the same way twice. That's what astronomers saw when they pointed their instruments at a peculiar sun over 1,000 light years away, now nicknamed TabbysStar. Its official name is KIC 8462852, but the mystery surrounding it has made it one of the most talked about stars in the sky. What makes TabbysStar so unusual is not that it dims, it's how it dims. Stars dim all the time. That's how we detect exoplanets. A planet crosses in front of its parent star, blocking a small portion of the light. It's a predictable dip, regular, rhythmic, always the same. A tiny blip, maybe 1% or so, lasting a few hours, repeating every few days or weeks, like clockwork. But TabbysStar doesn't do that. It plunges in brightness, sometimes by 15%, sometimes over 20%. These are massive fluctuations, like turning down the brightness on your phone from full blast to dim mode with no warning, then turning it back up again, then down again, then nothing for days. And it does this with no pattern. The dips aren't evenly spaced. The depths vary wildly. Some last days, some last only a few hours. There's no regularity at all, just chaos. So, naturally, astronomers tried to figure out what could possibly cause it. First guess? A planet. Maybe a big one, maybe with rings, maybe multiple planets in strange orbits. But no, nothing matched the data. Even Saturn-sized planets can't block that much light, and nothing explained the erratic timing. Next idea, comet fragments. A huge cloud of icy bodies breaking apart and spreading a dusty veil around the star. That sounds reasonable, until you do the math. To dim the star by over 20%, you'd need an absurd number of comets, thousands, maybe tens of thousands, breaking apart in exactly the right configuration, drifting in and out of view over years without leaving clear infrared signatures behind. That's unlikely. Some researchers proposed giant disks of dust. Others speculated about circumstellar material, maybe a debris field from a planetary collision. But none of these fully fit. They all explained part of the data, not the whole story, which led some astronomers to whisper a possibility that's rarely spoken in professional circles. What if it's artificial? Not in the aliens are coming sense, but in the sense of a technological structure, something built, not born. The idea was sparked by a concept proposed decades earlier by physicist Freeman Dyson, a Dyson sphere. The idea that a sufficiently advanced civilization might construct a swarm of structures around their star to harvest its energy, not a solid shell, but a cloud of solar collectors, satellites, mirrors, sails. If something like that existed partially built, maybe broken, maybe in motion, it could dim a star's light in unpredictable ways. Tabby's star, some said, looked a little too much like that. The media ran with it. Headlines flared. Alien megastructure discovered. But within the scientific community, things stayed cautious. Most researchers believe the explanation is likely natural, but we haven't yet found the right one. Still, the fact that we can't rule out something artificial keeps the mystery alive. And here's the part that deepens the puzzle. The more we observe Tabby's star, the weirder it gets. The dimming continues, but now it's accompanied by long-term fading, a slow, steady drop in overall brightness over the years. That's not something comets or dust would usually cause. There's no significant infrared emission, no heat signature that suggests dust. There's no periodicity, which rules out most orbital explanations. And nothing in the spectral data points clearly to gas, collisions, or stellar instability. In other words, we still don't know. As of 2025, despite years of continuous observation by telescopes on Earth and in orbit, Tabby's star remains one of the strangest objects ever recorded in the night sky. But perhaps the most remarkable thing about this mystery is how it was found. The data came from the Kepler Space Telescope, which collected light curves from hundreds of thousands of stars. The Kepler mission was an engineering marvel, but the raw data was only the beginning. It took human eyes to notice the anomaly. A citizen science project called Planet Hunters invited volunteers to sift through the brightness graphs, and it was an amateur who first spotted the bizarre dips and flagged them for deeper study. That's what started the scientific inquiry. A regular person looking at an unusual squiggle on a chart, wondering, what is that? And in that moment, the mystery of Tabby's star was born. Since then, it's become a symbol, a reminder that the universe is still full of surprises, even in the era of high technology and big data. It tells us that not every anomaly has an easy answer, that sometimes, when we see something that breaks the pattern, we shouldn't discard it. We should pay attention, because nature has a habit of showing us the limits of our imagination. In a way, the story of Tabby's star is not about aliens or comets. It's about curiosity, about the power of observation, about the idea that sometimes mystery arrives not with a bang but with a dimming light. And it leads us to a deeper question. If this star can do something so strange, with no clear cause, how many other mysteries are we still missing? How many weird stars are out there, flickering in ways we haven't yet learned to notice? In the next part of our journey, we'll encounter something even stranger. Not a star, but a shape. A radio signal in the sky that doesn't come from a point, but from a circle. A circle of such size that it spans galaxies. A shape we never expected to see. A puzzle with no clear source. Odd radio circles. We'll look at them next. Sometimes, a new mystery doesn't announce itself with a bang. Sometimes, it just appears quietly, unexpectedly on a computer screen. Something no one predicted. Something no one asked for. Something that shouldn't exist. This is the story of the odd radio circles, or ORCs. Imagine you're an astronomer combing through data from one of the most powerful new radio telescopes on Earth. You're not looking for anything dramatic, just surveying galaxies, mapping emissions, tracking the steady pulse of distant light. And then you see it. A circle. A perfect, glowing circle. Not a star, not a galaxy, not a planetary nebula, just a faint, symmetrical ring in the radio part of the spectrum drifting silently in the void. The first one was discovered in 2019 by a team using the Australian SKA Pathfinder telescope, and at first, no one could quite make sense of it. They'd never seen anything like it before, so they checked for instrumental errors. Maybe it was a glitch, maybe a smudge, a reflection, some kind of artifact. But then a second one appeared, then a third, and then a fourth, all of them shaped like enormous radio halos, some spanning over 1 million light years across. That's larger than the entire Milky Way galaxy. Each of these circles was invisible light. You wouldn't see them with your eyes, or even most optical telescopes. But in radio wavelengths, they bloomed into clear, unmistakable structures, rings suspended in space, glowing softly, with galaxies often found at their centers. So what are they? We don't know. Let's consider what they're not. They're not supernova remnants. Those are much smaller, and they're usually messy, chaotic, not smooth and symmetric like these. They're not planetary nebulae. Those are smaller too, and tied to dying stars. The ORCs don't line up with known stellar deaths. They're not gravitational lensing events. Those usually distort background light into arcs, not full circles. They're not radio lobes from active galactic nuclei, at least not in the traditional sense. Lobes tend to come in pairs, often stretched in opposite directions. But the ORCs are single rings, often centered around inactive galaxies. There's no jet, no activity, just the shape. In short, these things don't behave like anything else we've catalogued. Some researchers believe they might be the result of ancient shockwaves, colossal explosions from the centers of galaxies, expanding outward over hundreds of millions of years, long after the original cause has gone silent. Others suggest they could be remnants of enormous cosmic collisions, or even the fingerprints of unusual magnetic interactions on scales we've never fully studied. But every hypothesis comes with caveats. If they were ancient explosions, why do so few galaxies show them? If they were common, we'd expect to see more. If they were rare, why have we found several so quickly? Maybe they were always there and we just couldn't see them until now. That's the unsettling possibility. These odd radio circles only began to appear once we built instruments sensitive enough to detect them. And that raises a disturbing thought. What else is out there, hiding in plain sight, just waiting for us to build the right tools? It's worth noting that the telescope which first found the ORC's ASCAP was designed for wide-field surveys. It sees big chunks of sky at once, in deep radio frequencies, with excellent resolution. That combination is what made these discoveries possible. Not luck, just new vision. And when our vision changes, the universe changes with it. Here's what makes the ORCs even stranger. Many of them appear to have galaxies sitting dead center inside the circle. That suggests the galaxy might be the source, or at least somehow involved in creating the ring. But those galaxies aren't active. They're not spewing out jets or creating bursts of radiation. They look ordinary, dormant, uninterested. So are the rings left behind from some ancient activity long extinguished, like the smoke ring from a cannon fired eons ago? Or are we looking at something else entirely? Something not yet imagined? One suggestion, still speculative, is that we may be seeing the edges of three-dimensional bubbles in space spheres that, when viewed from our perspective, show up as flat rings. That's not so different from how we see the moon, a disk, though we know it's a sphere. If that's true, then we're not just looking at circles, we're seeing slices of vast, spherical events, each one bigger than a galaxy, each one radiating in a frequency band we've only recently started to understand. Think about that for a moment. These ORCs are new to us, not because they're new to the universe, but because we've only just become capable of noticing them. They've likely been floating there silent, ancient, slow-moving, while Earth went from molten rock to mossy oceans to modern cities. Now, finally, we can see them, and they don't fit. That's the recurring pattern here. The more tools we build, the more sky we scan, the more we find things that break our categories. And when something refuses to fit into our known bins, we're forced to either stretch the bin or make a new one. That's the real power of discovery, not just in adding more pieces to the puzzle, but in realizing that the puzzle itself might be a different shape than we thought. Odd radio circles remind us of that. They aren't loud, they aren't dramatic, they're quiet ripples in the dark, whispering that the cosmos still has secrets. And the only way we'll uncover them is by looking differently. In the next chapter of our journey, we'll step back and take in something bigger. Not a single structure, but a collection of galaxies spread across billions of light years, so vast that it challenges the very foundation of modern cosmology. It's called the Giant Arc, and if it's real, it breaks one of the most fundamental rules we thought the universe obeyed. We'll talk about that next. There's a principle in cosmology, an assumption so foundational that most models build on top of it without question. It's called the cosmological principle, And it says something deceptively simple. At a large enough scale, the universe should look roughly the same in every direction. Zoom out far enough, and all the lumps and bumps galaxies, clusters, filaments, voids should blur into a smooth and even spread. No preferred spots, no cosmic hot zones, just a quiet, isotropic universe. That assumption is crucial. It's baked into how we model dark energy, how we measure the age of the universe, how we simulate cosmic evolution. Without it, many equations collapse, which is why what was found in 2021 came as a shock. An astronomer named Alexia Lopez, working on her PhD, was studying a catalogue of quasars' ultra-bright galactic cores from the early universe. She wasn't looking for anything world-breaking, just mapping the positions of magnesium absorption lines, the spectral fingerprints of matter floating between us and the quasars. But when she plotted the data, she noticed something strange. A curve, not random, not noise, a structure, a long, gentle arc of magnesium-rich matter stretching across the sky. It spanned over 3 billion light-years from end to end. They called it the giant arc. And if it's real, if it's not an artifact or fluke, then it shouldn't exist. Why? Because it's too big. The cosmological principle tells us that, beyond a certain scale, about 1.2 billion light-years, the universe should become statistically uniform. Any structure larger than that starts to violate the assumptions that the universe is homogeneous. And yet here was a feature almost 3 times that size, sitting in a single slice of the sky. So, let's break this down. The giant arc isn't a wall of galaxies, like some other large structures we've found. It's more subtle, a chain of gas clouds and galaxy clusters traced by absorption patterns. But it's coherent. It curves in a distinct shape. It occupies a narrow redshift range, suggesting it's not just a projection of scattered objects. And importantly, it shares the sky with another anomaly, the Big Ring, a circular arrangement of gamma-ray bursts in roughly the same cosmic neighborhood. These are 2 different phenomena, but they're in the same patch of sky, at the same redshift, hinting at the same underlying scale. So now we have a problem, because if structures like these exist not just once, but repeatedly, it might mean that the cosmological principle isn't true, at least not everywhere. And that would force us to rethink nearly everything. Our models of cosmic inflation, the assumptions in our simulations, even the way we interpret the cosmic microwave background. It's like discovering that the ocean, which we thought was calm and flat at large scales, actually hides giant underwater ridges that stretch farther than tectonic plates. Maybe the universe isn't statistically smooth, maybe it's patchy, or lopsided, or shaped by deeper flows we haven't yet mapped. Now, to be fair, cosmologists are cautious. Extraordinary claims require extraordinary evidence, and single discoveries, especially ones made from small datasets, should be treated gently. Some argue the giant arc might be a coincidence, that our brains are wired to see patterns, that in a big enough sky, apophenia, the tendency to perceive connections where none exist, is inevitable. But others say the data's too consistent, that the arc isn't just visual, it shows up in statistical analysis too. It has a shape, a position, a presence, and if it holds up, it becomes one of the largest coherent structures ever identified in the universe. So what could form something like this? That's the big question. One possibility is that we're looking at the edge of a filament in the cosmic web, an unusually large one, stretched by early dark matter dynamics. Another is that this is the result of primordial density, fluctuations, ripples, from the first moments after the Big Bang, frozen into place by cosmic inflation. Or maybe it's something we haven't named yet, a relic of a past phase, a signature from an earlier epoch, a scar left behind by a force we haven't yet discovered. There's also the possibility, speculative, but not impossible, that we're seeing the residue of a collision between universes. If our universe is part of a broader multiverse, such an encounter could leave behind large-scale asymmetries. That's not the mainstream view. But in the face of data that refuses to fit, even radical ideas begin to whisper. Still, most cosmologists lean toward caution. More data is needed, better surveys, wider sky coverage, more redshift ranges, more precision. But here's what makes the giant arc so captivating. It reminds us that cosmology is still young. We've only been mapping the sky in detail for a few decades. Our tools are powerful, but limited. Our coverage is thin. Our models are built on assumptions that work until they don't. And in that space between what we assume and what we observe lies the beating heart of discovery. We've spent generations building a cosmic framework, a grand architecture of space and time, governed by general relativity, shaped by dark energy, sculpted by quantum fluctuations. And it works, spectacularly. But sometimes, a student plotting data for a thesis stumbles on something that doesn't quite belong, something that stretches too far, curves too cleanly, resists being ignored. The giant arc isn't a revolution yet, but it's a crack in the glass, a place where the model and the measurement don't line up, and that's the kind of tension that drives science forward. In the next part of our journey, we'll explore the opposite of structure, not something big, but something missing, a gap so vast, so empty, that it makes the rest of the universe look crowded, a region of space where there should be galaxies, but there are almost none. It's called the Boötes void, and its silence is as mysterious as any signal. The universe is not evenly filled. It's woven into a cosmic web, a vast network of filaments and nodes, where galaxies cluster like pearls on invisible strings. Between these filaments lie voids, huge, dark regions with fewer galaxies, less matter, and a kind of haunting silence. But even within that silence, there's usually something. Galaxies still drift through the emptiness, stars still burn, matter, though thinned out, still leaves its fingerprints. And then there's the Boötes void. It is one of the largest known voids in the observable universe, a sphere of space so vast and so nearly empty that it has been called the Great Nothing. Discovered in the late 1980s, it measures about 330 million light-years across. That's not a typo. That is over 300 million light-years of near-total emptiness, so large that if you placed the Milky Way at its center, our galaxy would drift for hundreds of millions of years without encountering anything. To put that in context, if you point your telescope at most regions of space, you'll see galaxies packed together in groups and clusters, sometimes thousands in a single image. But when astronomers pointed their instruments at Boötes, they found almost nothing. Only a few dozen galaxies scattered thinly across its volume. Yet based on its size alone, it should contain at least 2,000 galaxies, if the universe were behaving normally, 2,000 islands of stars. But instead barely a whisper. Why? What could create such a vast, silent gulf in the architecture of the cosmos? Let's start with what we know. Voids form naturally. In the early universe, tiny fluctuations in density caused matter to clump together under gravity, while underdense regions were gradually evacuated. Over billions of years, this created a frothy, sponge-like patterned dense nodes, connected by threads, surrounded by empty spaces. So, voids aren't strange. In fact, they're expected. But the Boötes void isn't just any void. It's unusually large, unusually empty, and unusually spherical. Most voids are irregular. They bleed into surrounding structures. They have fuzzy edges. The Boötes void, in contrast, is almost geometrically clean, a near-perfect bubble in the fabric of the universe. Some scientists have suggested that it might be the result of several smaller voids merging into a single, larger one. That's plausible. But the resulting shape should be messy, distorted, fragmented, not a smooth, empty ball. Others have speculated that the void is a kind of cosmic fossil, a region that, for reasons unknown, never formed galaxies in the first place. Perhaps its initial density was just low enough, its local fluctuations just mild enough that gravity never gained a foothold. But again, this stretches probabilities. The Boötes void is so extreme that even the most flexible models of large-scale structure formation struggle to account for it. And here's what makes it even more unsettling. The galaxies that do exist inside the void are strange. They tend to be isolated, unusually blue, and filled with active star formation, almost as if the emptiness around them triggered a kind of cosmic loneliness, a gravitational solitude that somehow ignited new life inside their cores. It's as if, in the absence of external pressure, these galaxies started burning brighter, or perhaps they're remnant survivors of a time when the void was not yet so empty. Either way, they're outliers, and they raise the question, what kind of environment creates galaxies like these? And what kind of environment erases everything else? There's a deeper philosophical dimension to this, too. The Boötes void isn't just a big empty space, it's a hole in the map of our assumptions. It suggests that even after centuries of cosmology, we still don't fully understand how the universe organizes itself. We assumed large-scale uniformity, but this void mocks that assumption. We expected a rich, interconnected cosmos. But here lies a sphere of almost complete isolation, as if a portion of the universe simply decided not to participate. And that invites stranger questions. Could this be the signature of something more exotic, a relic of primordial physics? A boundary left behind by early phase transitions in the universe's infancy? Or even a scar from some high-energy event, something that expanded and swept matter away like a shockwave, leaving only silence in its wake? More radically, what if voids like this aren't random? What if they serve a purpose we don't yet understand? Could they be the result of something? Or perhaps a canvas for something yet to be drawn? Of course, most cosmologists urge caution. Voids, even large ones, can be explained statistically. The universe is vast, and in a large enough dataset, rare things happen. The Boötes void could simply be the tale of a distribution, the unluckiest empty zone in an otherwise balanced cosmos. And yet, when you look at the sky and know there's a ball of emptiness the size of thousands of galaxies, it's hard not to feel something. A quiet awe, a gentle vertigo. It's like standing at the edge of a canyon so wide your voice is swallowed before it echoes. The Boötes void isn't just a scientific puzzle. It's a reminder that even in a universe filled with light, darkness still has room to grow. And sometimes, it grows bigger than we imagined. From here, we continue deeper into the silence. Our next mystery lies not in a structure, but in a blemish, a subtle distortion in the afterglow of the Big Bang itself. A region of the sky that is colder than expected, darker, less vibrant, and possibly not from this universe at all. It's called the cold spot, and some believe it may be the first evidence we've ever found for the multiverse. That's what we'll explore next. At the very edge of visibility, there's a kind of afterglow. It surrounds us completely, a faint whisper of heat from the earliest possible time, not from stars or galaxies, but from the universe itself, back when it was still young and blinding, barely a few 100,000 years old. This is the cosmic microwave background, or CMB, a nearly perfect snapshot of the infant universe, preserved across time as a map of temperature. When we look at it, we are seeing the oldest light in existence, stretched and cooled by over 13 billion years of cosmic expansion. And it's almost uniform, almost tiny variations in this ancient light are what seeded all the galaxies, stars, and structures we see today. The fluctuations are minuscule differences in temperature of just 1 part in 100,000, but they are incredibly important. They are the fingerprints of creation. But in 2004, something showed up in that fingerprint that wasn't expected. A patch of sky about 10 degrees across that was colder than it should be, not just a little, significantly. It was found in data from the Wilkinson Microwave Anisotropy Probe, and later confirmed by the Planck satellite with even greater precision. It's known simply as the cold spot, and even now, its presence is hard to explain. Let's be clear, fluctuations are normal. The CMB is full of hot and cold spots, slightly above or below the average temperature. But the cold spot is different. It's not just colder, it's too cold, and too wide, and too smooth. Statistically, it seems unlikely to be just a random fluctuation. The odds of something like this occurring naturally, according to the standard cosmological model, are somewhere around 2%. That's not impossible, but it is suspicious. So what could it be? The most conservative explanation is that it's simply a statistical fluke, just one of those weird things that happens when you roll the dice often enough. But if that were true, we might expect other anomalies of similar scale and intensity elsewhere in the sky. We don't see them. The second idea is that the cold spot might be the result of a massive void lying between us and that part of the sky. Here's how that works. When CMB photons pass through a large, underdense region of space, a cosmic void, they lose a tiny bit of energy due to the integrated Sachs-Wolf effect. It's a real process, subtle but measurable. In theory, a large enough void could cause a cold spot in the CMB by draining heat from the photons as they traverse it. And indeed, follow-up galaxy surveys did find a supervoid in that direction. An empty region roughly 1.3 billion light-years wide big. Yes, but perhaps not big enough. When modeled, this supervoid doesn't fully account for the observed depth and scale of the cold spot. In other words, the void might contribute, but doesn't explain everything. So we are left with the more provocative ideas. One of them is deeply speculative, but impossible to ignore. What if the cold spot is not just a blemish in the early universe, but a scar from something outside our own? What if it's the imprint of another bubble universe, one that collided with ours in the earliest moments of inflation? In some models of the multiverse, space doesn't just expand once and forever. It bubbles. It foams. Different regions of space-time inflate at different rates, branching off into separate domains, each with its own physical constants, its own particles, its own rules. Most of these regions never meet, but sometimes, maybe once in a trillion inflations, they do. If two bubble universes collided in the early epoch of inflation, the energy of that collision could leave a disk-shaped anomaly in the CMB, a region where the temperature is slightly off, where the symmetry breaks, where another universe left a bruise on ours. The cold spot fits the shape and characteristics that such a model would predict. It's not proof, not even close, but it's tantalizing, because if this idea is true, then we are no longer alone, not in the sense of life, but in the sense of reality itself. We live in one pocket of a far larger multiverse, and the cold spot might be the first evidence we've ever seen of that deeper cosmic architecture. But even if that theory proves false, even if the cold spot is just a statistical oddity or the result of unseen structure, its presence still matters, because it shows us where our understanding begins to wobble. The CMB was supposed to be smooth, predictable, modeled, and mostly it is, but then one part of it isn't. And that single deviant patch forces us to pause, to recheck our assumptions, to ask harder questions. That's how science advances, not by answers, but by anomalies. The cold spot isn't just cold, it's challenging. It's a place in the sky that refuses to conform, a quiet whisper from the beginning of time that says, there is more to know, and that whisper doesn't go away. It lingers. It lives inside the data, inside the models, inside the questions we don't yet know how to ask. That's why anomalies are precious. They point to places where the map doesn't match the territory, where the known and the unknown intersect, where the edge of understanding begins to glow faintly in the dark. In the next part of our story, we leave the grand canvases of the cosmos behind and zoom in tightly, strangely on a single star. One star, it looks normal at first glance, but its light spectrum contains elements that shouldn't exist, elements so unstable, so short-lived, that they should have decayed long ago, and yet they remain. A stellar mystery unlike any other. We'll meet it next. There are stars that challenge our understanding of gravity, stars that rotate too fast, shine too bright, explode too soon. And then there's one that challenges something even deeper, the periodic table itself. Its name is Przybylski's star. It doesn't pulse strangely. It doesn't warp space or flash gamma rays. From a distance, it looks ordinary, just another faint speck in the southern sky. But when you break apart its light, when you analyze its spectrum, you find something deeply bizarre. Its light contains the fingerprints of elements that should not be there, not because they're rare, not because they're exotic, but because they're too unstable to still exist. Let's step back for a moment. Every chemical element has a unique spectral fingerprint. a specific set of absorption lines in the light it emits or blocks. That's how we know what stars are made of. We decode their light, and when astronomers did this for Przybylski's star, they expected the usual suspects: hydrogen, helium, traces of heavier elements like calcium or iron, maybe some rare earth metals in the upper layers. But instead, they found promethium and technetium and other short-lived radioactive elements that, on Earth, decay in a matter of years, sometimes days, or even seconds. Promethium, for instance, has no stable isotopes. Its longest-lived form has a half-life of just 17 years. That means even if a huge quantity of it were somehow created in the star's atmosphere, it should vanish rapidly. Yet there it was. Over the decades, the spectral signature has remained, confirmed, reconfirmed, scrutinized, and still present. So how is that possible? There are only a few possibilities, and all of them stretch our models. Let's start with the mundane. One explanation is that these elements are being constantly replenished. That is, some process inside or around the star is creating them faster than they decay. But that raises another question. How? Radioactive elements like promethium and technetium are typically forged in supernovae or neutron star collisions, cataclysmic events involving massive stars and incredible energies. Przybylski's star is not exploding. It is a quiet, peculiar A-type star. Some have proposed that it might have a binary companion, possibly a neutron star whose high-energy emissions could be creating these unstable isotopes via nuclear transmutation on the star's surface. That's a compelling idea. A hidden partner, pulsing with invisible power, changing the chemistry of the visible star. But no such companion has been definitively observed. No X-ray pulses, no gravitational signatures, just silence. Another explanation is even stranger. Perhaps the star's magnetic field, extremely strong and complex, is playing a role. Przybylski's star is known to have a stratified atmosphere, where certain elements float to the surface and others sink, guided by powerful magnetic and radiative forces. This can cause chemical anomalies, pockets of rare earth elements accumulating at odd depths. But even this doesn't solve the main problem. It's not just that the elements are rare, it's that they shouldn't last. The radiation environment of a star should break them down. The passage of time should erase them, yet they persist. That's led to an even more speculative idea. Perhaps we are witnessing super-heavy elements, atoms, beyond the end of the current periodic table. Elements with atomic numbers in the 120 or 130 range. Elements that have never been seen on Earth. In theory, some of these ultra-heavy elements might exist in what physicists call the island of stability, a region of the periodic table where nuclear shell effects create longer-lived isotopes, perhaps stable for millions of years. If Przybylski's star somehow creates these, or captures them, they might decay into lighter radioactive elements like technetium or promethium, leaving a spectral fingerprint that looks familiar but comes from something deeper. Of course, we don't know for sure if the island of stability even exists. It's a theoretical haven predicted, but not yet observed. But that's what makes this star so fascinating. It sits at the intersection of astrophysics and nuclear physics, of what we can see and what we can barely imagine. It asks a question that no other star has asked. What if our periodic table is incomplete? That's not an easy question. It's not just about adding new rows to a chart. It's about acknowledging that our models of matter, the building blocks of everything, might still be missing pieces. And here's the haunting part. We've been observing Przybylski's star for decades. The anomalies are not new. They didn't appear yesterday. This star has been sitting in our catalogues, quietly violating expectations since the mid-20th century. It's as if it's been waiting for us to catch up. In many ways, it echoes the deeper theme of this journey. We assume the laws of nature are universal, that elements behave the same everywhere, that decay is decay, that stability is a property you can trust. But stars like this remind us, the universe isn't obligated to follow our rules. It follows its own, and sometimes it leaves behind a clue, a glowing ember of impossibility. a contradiction too persistent to ignore. Przybylski's star is one such ember, and we don't yet understand what it's trying to tell us. But we're listening. In the next part of our story, we follow something that isn't a star. It's a traveler, a visitor from the deep interstellar dark, not a planet, not a comet. Something that entered our solar system on a path no object had taken before and left just as mysteriously. It came without warning. It behaved like nothing we've seen, and it may not come back. It's called Oumuamua, and its strangeness defies classification. In October of 2017, a telescope in Hawaii spotted something drifting through space. At first, it seemed ordinary, a faint point of light, tumbling silently in the sky. Just another asteroid, perhaps a leftover shard from the solar system's messy past. But very quickly, it became clear. This object didn't belong here. Its trajectory was all wrong. Instead of looping in an ellipse around the sun, like every known asteroid or comet, this object was on a hyperbolic path, curved not inward, but outward. That meant only one thing. It came from beyond the solar system, and it was already on its way out. It was the first confirmed interstellar object ever observed. Its name, given by the International Astronomical Union, was Oumuamua, a Hawaiian word meaning scout or messenger from afar, arriving first. And it lived up to the name, because the closer astronomers looked, the stranger it became. Most comets, when they approach the sun, heat up and release gas, forming visible tails or halos. Oumuamua showed none of that. No coma, no trail of debris, no obvious signs of outgassing. Just a faint, rotating light source. Yet here's the twist: it was accelerating, very slightly, but measurably. It was moving faster than gravity alone could account for. That made no sense. Something was pushing it. In comets, this kind of acceleration is common. Jets of vapor act like tiny thrusters. But again, Oumuamua had no visible jets, no emissions, just silence. So what was causing the extra boost? Let's talk about shape. The object's brightness fluctuated dramatically up to a factor of 10 as it tumbled. That suggests a very elongated shape, possibly cigar-like or perhaps a flat pancake geometry, something unlike any natural body we've ever seen. Models based on the light curve suggested that Oumuamua could be up to 10 times longer than it is wide, a cosmic needle, a shard of mirror, or something else. At this point, theories began to multiply. Some scientists proposed it was a fragment of a disrupted planet shaped into a sliver by tidal forces and flung out of its home system billions of years ago. Others thought it might be a type of exotic, hydrogen-rich comet, one that releases only invisible gases, evading detection. Still, others suggested it was a piece of cosmic ice so unusual that it sublimates without the usual signature. All of these explanations had problems. They required fine-tuned parameters, strange initial conditions, or materials that are at best hypothetical. And so, one scientist, Avi Loeb, proposed a different possibility. What if Oumuamua wasn't natural at all? What if it was artificial? A thin sheet of material, no thicker than a millimeter, designed to harness radiation pressure from starlight, a light sail drifting between the stars. Not a spacecraft in the traditional sense, more like space debris, a shard from a broken probe, a fragment from some long-dead interstellar civilization. It was a bold claim and a controversial one. The astronomical community largely rejected the idea. There was no direct evidence. The data were limited. Oumuamua had already vanished from view, too faint to track further. But the timing mattered. We only saw the object after it had already passed Earth, racing away from the Sunday. We had just 11 days to study it closely before it faded. It came, it passed, it left, leaving behind only questions. Here's what makes this moment unique. For the first time in human history, we had detected something from another star system, inside our own solar system. Not a radio signal, not a distant light, a thing, an object we could observe directly. And we were not prepared. No missions, no probes, no interception plans, no immediate way to capture or follow it. All we could do was watch it recede into the dark, vanishing into the background sky like a leaf carried away by wind. And still the mystery lingers. Oumuamua wasn't bright. It wasn't large. It didn't blaze across the sky like a comet, but its trajectory, its acceleration, and its silence make it one of the most enigmatic things we've ever recorded. It forced us to confront a possibility that had always been theoretical, that interstellar debris or perhaps interstellar artifacts might pass through our solar system more often than we realize, and we might only be seeing a tiny fraction of them. Indeed, in 2019, another interstellar visitor arrived, Borisov, a more traditional-looking comet. It had the hallmarks, a coma, a tail, a behavior that fit our expectations. But Borisov didn't erase Oumuamua's strangeness. If anything, it emphasized it. Because while Borisov behaved like a visitor from far away, Oumuamua behaved like a messenger from something unknown. Maybe natural, maybe not. The truth is, we don't know, and that's the power of it. Oumuamua reminds us that the cosmos is not a closed room. It's a corridor, a place where things pass through, where travelers leave traces without explanation. We may never know what it was, a shard of ice, a splinter of rock, a forgotten piece of alien engineering. But we saw it, and that alone changes things, because it proves that we are not alone in our aloneness. We share space with other systems, other debris fields, other histories. Some of them send messages, others send objects, others pass silently. And in the silence, we are left to wonder, where did it come from? What shaped it? Was it ever watched as it now watches us? In the next chapter, we'll turn to things that shout, not whisper, explosions so fast, so bright, so utterly unfamiliar that they had to be given a new category altogether. They are not supernovae. They are FBOT's fast blue optical transients. And the first one we found was called the Cow. We'll explore what it was and why it still has astronomers baffled next. In June of 2018, something exploded. Astronomers around the world picked it up, a sudden burst of light in a relatively quiet corner of the sky. It came from a galaxy about 200 million light-years away. Nothing unusual at first glance, until they looked closer, because this was no ordinary supernova. It was too fast, too bright, too blue. It rose to peak brightness in just a few days, far quicker than any standard stellar explosion. And it reached that brightness with an intensity that rivaled the most energetic events we know. For comparison, typical supernovae take weeks to reach their full luminosity. This one lit up almost overnight, and then it faded, also too quickly, as if whatever had burned so hot and so violently was already dying before it had fully begun. Astronomers didn't know what to call it, so, by the automated naming system, it became AT2018 Cow. The Cow, that was the name, and soon it would become infamous. Let's walk through why. The Cow was the first well-observed member of a class of explosions now known as FBOT's fast blue optical transients. They're rare, elusive, fleeting, and they don't behave like anything else. Their light curves are wrong. Their spectra are wrong. Their timelines break the usual rules. And above all, they don't tell us what caused them. With the Cow, the initial assumption was simple. It must be a strange kind of supernova, a massive star, reaching the end of its life, collapsing under its own weight, detonating in a blaze of thermonuclear fury. But that explanation quickly ran into problems. The spectra didn't show the usual heavy elements. No iron peak, no typical calcium lines. Instead, there was an excess of high-energy radiation, X-rays and gamma rays, unusually persistent for such an event. And at the center of the fading light, there seemed to be something enduring. Not dust, not silence, but a heartbeat. A pulsing, steady emission that hinted at a central engine, something left behind after the blast. Perhaps a newborn black hole, perhaps a rapidly spinning magnetar throwing off waves of radiation as it cooled. Whatever it was, it refused to fade quietly. And this changed everything, because typical supernovae don't leave such visible, active cores, not this fast, not this loud. The cow was doing something new, or perhaps something very old that we had never caught in the act before. In the years since, more FBOTs have been detected. They have names like the camel, the koala, the finch, all of them quick, all of them hot, all of them bright, and all of them unsettlingly unfamiliar. Some hypotheses have emerged. One possibility is that these are tidal disruption events when a white dwarf or neutron star gets too close to a massive object, like a black hole, and is torn apart. But that scenario doesn't quite fit the speed. Another idea, a failed supernova, where the star collapses directly into a black hole and the remaining envelope is blasted outward by fallback accretion. That would explain the brightness, the X-rays, and the persistent signal. Still, there are inconsistencies. FBOTs often occur in star-forming galaxies, but not always. Some seem to come from regions with little gas or dust places where massive stars shouldn't even exist. Others fade too fast to get good data, so we're left with questions. What kind of star dies like this? What kind of collapse leaves behind a beacon? Why are these events so fast, so much faster than physics says they should be? And perhaps most intriguing, have we been missing these all along? FBOTs may be common, but because they vanish quickly, we may have overlooked them for decades, centuries, even. Our telescopes, our cadence, our classification systems weren't designed to catch things that live and die in the span of days. But the night sky is changing. With the rise of time-domain astronomy observatories that scan the sky night after night, mapping its changes in real time, we are starting to see more of these strange explosions. They're not just flukes, they're a pattern, a new category of stellar death, or perhaps a new kind of birth, because that's the other theory. Some scientists believe FBOTs may not be endings at all, but beginnings the moment a black hole is born, or a neutron star spins to life, screaming in magnetic rage before settling into silence. It's a beautiful symmetry, that something so violent could also be a kind of emergence, that the universe doesn't just create in calm, slow waves, but sometimes in bursts, in ruptures, in sudden, luminous acts of transformation. The cow was our first real glimpse of that, a flash in the dark, a question in the shape of light, and maybe a signal, not from an alien civilization, but from nature itself, reminding us that the death of a star can be many things, a story we've barely begun to understand. And perhaps the deeper message is this: we keep trying to classify the sky, to group it, to box it, this kind of star, that kind of explosion, these rules, those timelines. But the universe isn't a filing cabinet. It's a poem with verses we haven't yet learned to read. And sometimes, the poem throws us a line we've never seen before, like the cow. And all we can do is stare and write it down and wonder. In the next chapter, we'll turn from explosion to age. Not something newly born, but something impossibly ancient. A star whose estimated age appears older than the universe itself. And yet, there it is, burning quietly, waiting for us to make sense of the math. We'll meet the so-called Methuselah star next. In the quiet constellation of Libra, not far from the celestial equator, there burns a small, faint star. It's not particularly bright, not particularly large. It doesn't pulse, explode, or distort the space around it. Most telescopes pass over it without a second glance. But this star carries a secret. According to some estimates, it is older than the universe itself. It is officially named HD 140283. Informally, it's known as the Methuselah star, a poetic nod to the ancient figure in biblical lore said to have lived longer than any other human. But even that legend pales beside this star's supposed age, because HD 140283 appears to be more than 14 billion years old. And that is a problem. The currently accepted age of the universe, based on measurements of the cosmic microwave background, the expansion rate of galaxies, and models of cosmic inflation, is about 13.8 billion years, which means this star shouldn't exist, or at least not in the form we see it today. So, Let's explore how something like this could even be possible. Methuselah is a population 2 star, a term used for some of the oldest stars in the galaxy. These stars are extremely low in metals, meaning they formed before the universe had time to enrich itself with heavier elements from generations of supernovae. That's already a clue. It tells us that this star formed very early, likely in the first billion years after the Big Bang. It's a relic from a time when galaxies were still assembling, and the cosmic web was just beginning to take shape. Astronomers determined its age using a variety of methods: parallax measurements to gauge its distance, spectroscopic analysis to study its composition, and stellar evolution models to estimate how long it's been burning. And the numbers don't add up. Initial studies pegged its age at around 14.5 billion years, with error bars that still placed it above the age of the universe. Later refinements pulled the estimate slightly lower, perhaps 13.7, but even that cuts painfully close to the edge of cosmology. It's as if the star is standing on the threshold of time itself, whispering, "I was here before it all began." Now, to be clear, most astrophysicists do not believe the Methuselah star actually predates the Big Bang. That would require a complete overhaul of modern cosmology. Instead, the leading consensus is that we're underestimating the uncertainties in distance, in chemical makeup, in the models of stellar aging. Perhaps it's younger than we think, or perhaps the universe is older than we've calculated. But even with all that caution, the Methuselah star remains uncomfortably old. It is a crack in the paint of the standard model, a reminder that our tools, though powerful, still depend on assumptions. And sometimes, those assumptions bend more than we realize. So what are the possible explanations? One is that the star's distance has been misjudged. A small error in parallax can ripple through the age calculation, making it appear older than it really is. Another possibility lies in its metallicity. Because it contains such a low abundance of heavier elements, it may evolve differently than most stars. Its internal structure, its nuclear fusion rates, its energy transport, all of these could affect how fast it burns through its fuel and how we interpret its stage in the stellar life cycle. Then, there's the matter of initial helium content. If Methuselah formed with a slightly different ratio of hydrogen to helium than we assume, its aging curve could shift. And yet, even when all these factors are adjusted within reasonable margins, the star still seems exceptionally ancient. So we're left in a state of limbo, not a contradiction, not quite a paradox, but a tension between what the star appears to be and what the universe is supposed to allow. And it forces us to ask harder questions. What if our models of stellar evolution are incomplete? What if the early universe produced stars differently than we thought? What if time itself, cosmic time, the ticking heartbeat of the universe, is not as straightforward as we believe? There's something humbling about this. That, in all our maps of galaxies and black holes, in all our measurements of redshifts and gravitational waves, a single, quiet star might be what upends the whole story, because it doesn't burn like a mystery. It burns like a witness, a survivor of a cosmic childhood we can only glimpse in theory. It's not the only ancient star, of course. The Milky Way is filled with halo stars and globular clusters that formed in the deep past, but most of them fit neatly within the cosmic timeline. Methuselah refuses to fit, and that makes it precious, because in every scientific era, there are anomalies that feel small, until one day they aren't. One day, they become the catalyst, the crack that reveals a deeper layer. That's what this star might be, a quiet question hiding in plain sight. And perhaps, most beautifully, it reminds us that age is not clarity, that something can burn for billions of years and still remain mysterious. And that maybe the stars are not just lights in the sky, but chronicles, storing information we haven't yet learned to read. In the next chapter, we'll look at the bigger picture. We'll return to the meta level. Because now that we've toured these 10 anomalies, these things that should not exist, we have to ask a deeper question. Are they all isolated, random, or are they connected? Could these unexplained phenomena be fragments of a larger pattern? A signal not in any single mystery, but in the collective existence of so many? That's what we'll explore in Part XI. We've now walked through 10 cosmic riddles. Each one is strange. Each one, standing alone, seems like an outlier, a glitch in the data, an edge case, an exception. The wow signal, a radio whisper with no origin. TabbysStar dimming unpredictably, like something built, not born. The odd radio circles, symmetrical halos in radio light, larger than galaxies. The giant arc, a structure so vast it bends the rules of cosmology. The Botti's void, a chasm of nothingness where thousands of galaxies should reside. The CMB cold spot, a scar in the sky, possibly from another universe. Przybylski's star, hosting elements that shouldn't last more than days. Oumuamua, an interstellar object moving like it had purpose, but making no sound. The cow, an explosion too fast and too bright to name. And the Methuselah star, a quiet flame older than time. Taken one by one, each of these is fascinating. But together, they form a constellation of uncertainty. And that raises a profound question. Are we looking at 10 isolated puzzles? Or are these the fragments of a deeper truth? What if we're seeing not a series of unrelated anomalies, but the edges of a new paradigm? What if these are not bugs in the system, but features of a model we haven't yet built? This is not a new story in science. History is full of moments where mysteries piled up not loudly, but persistently until they tipped the balance. Consider the orbit of Mercury. For centuries, astronomers noticed that Mercury's orbit didn't behave exactly as Newton predicted. The shift, called perihelion precession, was tiny, just 43 arcseconds per century. But it was real, measurable, and unexplained. Most dismissed it as observational error. Some proposed an invisible planet, Vulcan, tugging Mercury with hidden gravity. But it wasn't until Einstein's theory of general relativity came along that the mystery dissolved. The warping of space-time accounted for the discrepancy perfectly. The anomaly had been a clue, a quiet hint from the universe that our understanding was incomplete. The same happened with quasars. When they were first discovered, they seemed impossible point sources of light that outshone entire galaxies, yet had stellar-like properties. For years, they resisted explanation, and then we realized they were supermassive black holes, feeding on galaxies from within, their jets glowing across time. They didn't break the model, they expanded it. Or take the discovery of dark energy. In the 1990s, two teams independently measured the redshift of distant supernovae. They expected to find that the universe's expansion was slowing. Instead, they found it was accelerating. This was not just surprising, it was a revelation. It forced the insertion of a whole new component into the cosmological model, dark energy, now believed to account for almost 70% of the total energy content of the universe. In all these cases, the key was not a single anomaly. It was the accumulation, a pattern, a weight, a quiet gathering of tensions that eventually required a shift. And so we must ask, are we living in another one of those moments? Are these 10 mysteries these stars, signals, voids, and arcs trying to tell us something? Not through a single scream, but through a shared whisper. Maybe we are on the edge of something. Maybe we're already seeing signs of a new framework, one that better explains high-energy transients, cosmic structure, interstellar dynamics, and the deep past of matter. Maybe we need to let go of the expectation that the universe should be tidy, that it should fit neatly into models built on earthbound thinking. Because the universe has never been tidy. It was born in chaos. It evolved in turbulence. It has always resisted simplification. And the anomalies are not accidents. They are invitations. Each one says, look again, think differently, step beyond the known. This is the real message behind the unexplained. Not that the current theories are wrong, but that they are incomplete. And that incompleteness is a feature, not a flaw, because science does not advance by confirming what we already know. It advances by confronting what we don't, by listening to the silence between the data points, by following the deviations, by embracing the discomfort of unknowing. There is a beauty in this, a kind of cosmic humility, the realization that Even after centuries of observation and theory, we are still at the beginning of understanding the universe. These anomalies are not obstacles. They are lanterns, flickering lights on the edge of the map, marking places where we should look more closely. And if history is any guide, it is in those places, those dark corners, where current theory falls short, that the next great revolutions will be born. In the final chapter of this journey, we'll shift perspective once more. We'll pull back from the data, from the stars, from the signals, and we'll ask a deeper question. What does it mean to live in a universe filled with questions? What does it mean to be conscious, mortal, curious creatures floating through a cosmos we barely comprehend? What is the emotional, philosophical, human weight of knowing that the sky is filled not just with answers but with echoes we have yet to understand? That's where we'll go next. And that's where this story truly finds its center. The sky has always been full of questions. Long before we had telescopes, equations, or language precise enough to measure, we looked upward and felt it the vastness, not just of space, but of something else, something deeper, a kind of invitation to wonder. Now, after 12 chapters, 10 anomalies, and one long journey through the edges of science, we are left with a new kind of question. Not what are these strange things in the sky, but what does it mean that they're there at all? What does it mean that the universe refuses to be fully explained? That even after centuries of physics, we still find structures that are too big, stars that are too old, objects that move like nothing we've ever seen before? We could say, as some do, that it's just a matter of time, that we'll figure it out, that the data will improve, the models will refine, and the puzzles will resolve. Maybe, but maybe the mystery isn't just a temporary condition. Maybe the mystery is the point, because every time we uncover something that doesn't fit, we are being shown gently, persistently, that our understanding is still evolving, that our models are just approximations, that our perspective, as vast as it feels, is still incredibly narrow. We live on a rocky world, orbiting a yellow star, drifting through a spiral galaxy among trillions of others. We are made of atoms that were once inside stars. We breathe oxygen forged in ancient fusion. We think, we ask, we wonder, using brains shaped by evolution on a planet that barely registers on the cosmic scale. And yet, we try to understand everything. We build instruments that stretch our senses. We listen to radio waves from stars. We map the faint glow left behind by the Big Bang. We name, categorize, simulate, and still the sky pushes back, with silence, with cold spots, with stars that contain impossible elements, with signals that appear once, then never again, with rings, arcs, and voids that whisper, "You are not finished learning." There's something beautiful in that, because it means the universe is not passive. It is not a solved equation. It is alive with resistance. It speaks in riddles. It leaves trails. It challenges every certainty. And in doing so, it teaches us something not just about physics, but about ourselves. To be human is to live inside the unknown. To be curious is to make peace with uncertainty. To be a scientist, a dreamer, a thinker staring at the stars, is to understand that knowledge will always be partial and that this is not failure. It is the shape of growth. We don't learn in straight lines. We learn in spirals. We return again and again to questions we thought we had answered, only to find they've changed or we have. And the universe waits. It doesn't rush us. It doesn't explain itself. It just continues patient, strange, magnificent. Think of Jerry Emmon in a quiet office, circling a radio signal with a red pen, writing one word, wow. Think of Tabetha Boyajian, staying up late, wondering why a star refused to follow the rules. Think of Alexia Lopez, seeing a cosmic arc that bent more than just light, it bent the very principle of uniformity. Think of you, right now, sitting somewhere on this pale planet, listening to a voice tell stories about impossible things, and asking, what does all this mean for me? That is the real heart of this journey, not the data, not the physics, but the feeling, The feeling that something enormous is unfolding around us, that we are witnesses, not just observers, participants in a story that began long before us and will continue long after, and yet still somehow includes us. When we say the universe is mysterious, we are also saying we are part of that mystery. We are not outside it, looking in. We are inside it. We are stardust, organized for a little while, trying to understand itself. And maybe that's why the anomalies matter, not because they break the laws, but because they show us the edge of what we've made so far. They are moments when the curtain lifts just slightly, when something impossible makes itself known, when the cosmos reaches out not with an answer, but with a question. What if this? What if more? What if everything you've built is only the beginning? That is what science is, at its best. Not the memorization of facts, but the slow, reverent dance with the unknown. Not to conquer it, but to learn how to move within it. So, what now? We've reached the end of this series, but not the end of the mystery. Because out there right now, new data is being recorded. New stars are dimming. New objects are passing silently through our solar system. New voids, new arcs, new echoes from the beginning are waiting to be seen, to be misunderstood, to be questioned. And you who listened to this, who stayed through the whispers and the wonder, you are part of that process now. The universe doesn't just belong to scientists in observatories. It belongs to anyone who looks up and asks. And tonight, maybe you will. Not for an answer, but for a reminder that mystery is not the absence of meaning. Mystery is what invites meaning into being. It's what makes the stars worth studying. It's what makes the cosmos worth singing about. And it's what makes your life, your brief, burning, miraculous life, something greater than random atoms. Because here you are, in this moment, on this world, asking questions. And that may be the most extraordinary anomaly of all.